Okay, so hi, good evening, good morning, good afternoon, whatever time you may watch this. So I'm sorry I could not hold a synchronous session for tomorrow or I guess later, since due to personal reasons. So there has been sort of emergency that I need to uh, make asikaso. So the goal of the synchronous session for tomorrow was supposedly to focus on the hammer wrap exercises for weeks 7 and 8. Some of you in the previous synchronous session has said that they had a little trouble uh, finding out or understanding what is being asked for the exercises. So we can first start with the first exercise, make it double. So uh, the goal here is to basically convert the given singly linked list implementation to a doubly linked list implementation. So the input is basically commands. So the first number is basically the number of commands. And starting from an empty doubly linked list, we want to insert the following elements and then delete the following elements as well. So what you just have to implement actually or modify is at least the insert and the delete commands, such that the previous nodes, the proper previous nodes are updated for the existing nodes in the list. So as you can see now, only the next pointer for each linked list node is being modified by the insert and the delete operation. So if you have some trouble visualizing how to insert elements in a W linked list, you can of course go to visualalgo.net. They have a lot of different visualizations here. So that's why they are called Visual Algo. So you can look at the linked list module and select the W linked list. So that brings us here. So we can almost follow the things here. So something to note about the insert and the remove operations. You can consider inserting at the start and the end as special cases, and inserting at the middle as the general case. So for example, when we want to insert this element 11 to a doubly linked list, you can follow the pseudocode here. So starting with the new node that we want to insert or new vertex we want to insert, we first make our void vertex point to what is pointed by at the head. So this is inserting at the start of the list, similar to the first uh, similar to the first case or sample input. So we have originally a 25 in the list, and then so our new node points to that node first, and then if the head exists, the previous pointer, so head.previous should point to the new node since it's now the last one there. And then the vertex that has been added is now the new head. So it's now at the start. So if you want to add another number, let's say, okay, so that's a little embarrassing. But of course here, if you want to insert another number at the start, the process is virtually the same since we only deal with the starting element. Now, when we want to insert at the middle, say at index 5, so like the singly linked list, which I have described in the lecture notebook, before you can insert an element, you have to traverse through the linked list in order to reach the proper index. So that also happens here. So since I specified that I need to insert at index 5, I need to traverse through 5 elements first, or actually 4 elements first, because the fourth element should point to the new node. But before we do that, we have to have our vertex point to the node after that previous node, since we might lose our connection. So if we immediately, or sige, tagalogin na. If si 17 nagturo siya agad kay 90, wala na tayong nakaturo kay 57. So we have to make 90 point to 57 first before we transfer yung next pointer kay 90. So look here, so yung previous ni 57, nakapoint na siya kay 90. Okay. So yung nangyari is, yung after ni vertex, ipo-point natin sa after nung original na previous. And then yung after the vertex points to the previous na. And then we transfer the pointer of 70 to point at 5. So visually, and then we point back. So visually, yung mangyayari is maybe ganyan. So hopefully that clears things up a bit. So so ginamit dito is the head and tails are actually just pointers. Although you can also implement it as a sentinel node, which is what I did here. Linked list node sila, hindi lang sila basta-basta pointer. So if you have the Introduction to Algorithms book by Corman et al., CLRS, there's actually an implementation of Adobe linked list there. Although it's a pseudocode, it's much more simpler because it uses our Sentinel nodes. Kasi ang nangyari dito, basically, special case yung pag-insert sa start and sa end, since yung head and tail natin, kailangan natin i-modify. However, if the head and tail are actually, if we consider the head and tail actual nodes, we can treat our linked list, lalo na kahit empty siya, as still having 2 more elements. So yung insert and delete operations natin, hindi sila special case pag nag-insert at saka remove tayo. So, eto. Pakita ko na lang din yung visualization ng pag-remove. So, medyo mabilis. So, what happened here is that yung head pointer ko, not visualized, may tuturo siya doon sa susunod kay original na head. And of course, we need to have a temporary pointer dun sa original na value ni head. Kasi if we don't do that, mawawalan tayo ng pointer sa kanya. So, hindi natin siya ma-delete. So, the same happens when we delete at the tail. We need to point something to the what's previous sa tail before actually deleting it para hindi tayo mawalan ng reference sa kanya. When we remove an element in the middle, similar sa insert, kailangan muna natin mag-traverse dun sa list. So, tatraverse tayo hanggang sa second if we want to remove the one at index 3. So, the one to be deleted is this one in the middle, so 70. So, we need to have temporary pointers for the element before and the element after. Kasi pagka-delete natin dito, baka mawalan tayo ng pointers to each. Mag-break yung link. So, bago natin tanggalin si 70, kailangan niya munang ipamana, basically, yung pointer niya to 90 kay 14 and yung pointer ni 14 kay 90 before siya tuluyang tanggalin. So, basically, sipin mo lang if you're in sort of organization and you have to leave, kailangan to be more professional, kailangan parang may turning over doon sa papalit sa'yo. So, yun lang naman for the W link list. So, hopefully that clears things up about the exercise. So, basically, implemented na yung print functions it relies on using the previous pointer starting from the tail. Tatraverse lang siya using the previous pointer. So actually, ngayon, pag niran mo to ngayon, ang makikita mo lang is yung print forward since hindi natin minodify yung mga previous pointers. And kung gusto mong i-hack, but of course, this is a very brute force method. Pag si tail.rev, ginawa ko siyang equal kay llhead dot next. So, ilan na ba yung elements? Supposedly 5. So, kailangan ko na 5 next. 1, 2, 3, 4, 5. So, pag nilagyan ko na naman si tail.rev, pag niran ko yung code, dun sa print reverse, makikita natin si 25 na nauuna dito. So, basically, kung itutuloy mo pa yung brute force dito, dagdagan mo ng isang prev, and bawasan mo ng isang next. And makikita mo yung next na element. So, basically what this means is pag naayos mo yung mga previous pointers dito sa implementation, you should get the right answer. So, I think we can move on to the next exercise. 2 queues and 1 stack. So, for the lecture notebook na pinrovide ko, nagbigay ako ng example dito of how to implement a stack or how to implement a queue using 2 stacks. So, dito siya sa making things interesting. So, whenever we need to dequeue, i-empty muna natin yung stack natin para makuha natin yung first element. Since sa stack, pag nagpo-push tayo sa stack, lagi siya napupunta sa pinakataas. But if we want it to function as a queue, kailangan natin yung element na nasa pinakababa ng stack. So, ang gagawin natin is ililipat natin muna lahat ng elements sa kabilang stack. So, yung last element originally, siya na yung first element. And yun na, pwede ko na siyang tanggalin. Tapos ibabalik ko siya sa original stack. So, that's how you can implement a queue data structure using stack implementations. So, bakit kailangan malaman yun? Well, sinabi ko naman siya partially dito sa lecture notebook. So, hopefully, binasa nyo. And andito rin naman siya. So, we are putting ourselves in a situation na we have to program a device na medyo reduced yung functionality, which means na hindi lahat ng data structures implemented. Or, for example, sa future courses nyo, sa microcontroller, for example, ang available lang sa'yo actually is a stack. Walang queues, walang arrays, walang linked list na built-in. All you have is a stack. So, what if yun nga, I have a certain algorithm that uses a queue para maging efficient yung ating operations, but you only have a stack. So, at least, given this, hindi ka masa-stuck doon. Meron ka pa rin pwedeng gawin for that. So, to be more specific, yung input natin are commands. Pag push yung command, sasabihin kung alin number yung ipo-push. Tapos, pag nag-pop, ang expectation is lalabas yung pop element sa output. So, since nag-push ako ng 1, 2, 3, 4, 5, since stack dapat to, 5, 4, 3, 2, 1 yung output niya. And dito naman, may push, may pop, so may pagka. So, what you can see in the given template is a queue implementation na hindi nyo dapat gagalawin. But for those curious, this is a static array implementation actually ng queue. which assumes a maximum size ng queue. So since sa constraints, ang maximum number of elements ay 1,000, a static array na 1,000 elements yung actually ginamit. And I don't think I need to go into detail dun sa mechanisms nito. So here, for the stack, you need to define these three operations na as of now, walang ginagawa. So, ayun, when you have the queue, you don't have access, since dalawa yung underscore dito, you won't have access to these things. So, pag nag-q1 dot underscore underscore q ako, kung sabihin kong append ay, it wouldn't work. Dapat. So, runtime error. So, narito. Yeah. So, since underscore underscore q, you can't really access it. Ang kaya mo lang i-access yung mga walang underscore underscore. So, what you can use are these operations. So, sa push, I guess yung pinaka-analog niya sa Q is yung enqueue operation. Enqueue UE. So, pag ginamit mo yung function na yun, well, wala akong makukuha errors, pero wala output. So, ayun, siguro to start, pwede mong ilagay lahat ng queue operations dito na corresponding. So, yung partner ni Pop ay si the queue. And yung partner ni Peak ay si. So, given this, ayun, parang, no, hindi pa ba nag-save? Why is it not working? Okay. Mali. I have to rethink. Okay, I'm sorry. Ayan. So, instead of actually having a stack, ang nakuha natin na uh, output is basically that of a queue. So, nag-push 1, 2, 3, 4, 5. Ang lumabas sa output is 1, 2, 3, 4, 5 din, instead of the reverse where na-expected for a stack. So, ang gagawin mo dito, similar din sa nakikita natin dito. You need another queue and do some operations such that yung mapopop na element is yung element na gusto natin i-pop. Or yung mapipeak na element is gusto natin mapipeak. Or yung alternative, pwede mong baliktarin. Pag nag-push tayo, we ensure that napupunta siya sa front ng queue instead of the back ng queue. So, you can also do that supposedly with two different queues. So, note lang the constraint that basically yung pop operation dapat less than constant time siya. Ay, less than linear time siya. So, which means na dapat constant time. So, that's for exercise number 2. So next is exercise number 3, which is called Matchmaker. So in this exercise, ayun, may konting intro. So when we type in commands or equations, we often find ourselves missing or misplacing our braces, our brackets, or parentheses. So yung easy way is to count kung ilan yung opening braces, ilan yung opening brackets, ilan yung opening parentheses, and dapat mag-match siya dun sa number of closing na symbols. So basically, 2/3 of the cases, makakatch nun. But ang problem doon, what if ginawa ko siyang ganito? Yung naging katapat ng curly brace is a square bracket, and yung square bracket dito, yung naging katapat niya ng curly brace. So if we simply counted yung mga symbols, it would say na walang error. But in this case, may error kasi talaga. So we need to find a different approach. So one good hint here is that you will be needing one of the linear data structures na discussed. And another thing here, you can say that the last opening brace should have, or when we ever see a closing brace, dapat yung last na nakita nating opening brace is kapartner niya. So make of that what you will. So going further, yung input mo would look like this. And then, so kailangan mong basically i-ignore lahat ng non-parenthesis, non-bracket, or non-brace na input. And then, kuwari dito sa first example, lahat ng grouping symbols tama. So yung output is -1. And then in this next one, you would see at position 69, a closing parenthesis was found, but a closing curly brace. A closing curly brace is found, but a closing parenthesis was expected, but a curly brace is found instead. So basically, what that means is nagkapalit ng position itong curly brace na to at yung closing parenthesis dyan. Dito naman sa next output, so kulang ng closing parenthesis. And since 21 lang yung elements dun sa input array, yung error basically is found at location number 22. Then in this one, may extra closing brace located at index 35. So basically, ang kailangan nyo lang i-define dito is yung function na to. So by default, ang i-return niya is -1. So pagka nirun mo siya, basta lahat ng case na tama, magiging tama siya kasi parating -1.